So we have developed this code for a very simple solution to the mathematical problem of support vector machines. And I just want to review this and relate it to how you can do the same thing in Sklearn. And on the way, we'll also understand the role of the hyperparameter C or lambda that we've talked about in our previous videos. So let's start coding. As you can see, what we have a class over here called regularized perceptron. Okay. And but before I think before going into the code, let's talk about the mathematical problem. So we want to minimize with respect to the parameters of the linear discriminant. Those are the weight vector W and the bias term B. We want to solve this problem. W transpose W plus C over N summation I is equal to 1 to N and the hinge loss function, which is nothing but the max value of 0, 1 minus yi into f of xi. Okay, so that's what we want to solve. If you take the case of a single example, then what we want to do is first we want to minimize this error minimization, and we talked about how you can do that using gradient descent. But in an SVM, we also get this term, which is W transpose W. And more precisely, what we had talked about, the formulation that we talked about did not have a C term. It had a 1 over here, and it had a lambda parameter over here. So both of them are equivalent. Don't worry about that too much. But there is an addition term in a support vector machine. And when we take the derivative or we compute the gradient of this whole objective function with respect to W, this also adds a component to the gradient descent update, and we've talked about that in our previous lectures. To implement this equation, what we call a regularized perceptron, because that is what essentially a support vector machine is. So that's what we are going to call it, and it has a certain set of internal parameters. There's the step size of the support vector of the gradient descent. How many iterations do we want over the training data set? That's called the epoch. What is the starting weight vector? We just specify 0. What is the bias value? Again, we just can start with 0 or we can start off with any small random number. It doesn't really matter. Then we have the lambda parameter. What's the value of that? And then we have a margin, which is 1 in the case of a support vector machine. But Perceptron does not essentially have a margin, so this value is going to be 0. Okay, and the fit function over here, what that does is it uses a training data set, a training matrix XTR, along with the labels which are in YTR to do the optimization part. Remember, we talked about that a machine learning model has three parts: representation, evaluation, and optimization. The representation bit is simply f of x equal to W transpose x plus b. So that we implement over here in the score function. So that gives us a decision function score of a given machine learning model of this linear discriminant. And we can obtain labels, discrete labels from this score by basing it on the sign of whether f of x is greater than 0, then it belongs to the positive class, otherwise it belongs to the negative class. So the representation bit is implemented, you can say, in these two functions. We already have a feature representation x that is given as input, so that is done outside of this code. And but that's the essential representation bit. Then we talked about the evaluation bit, and evaluation is simply how we measure error over the training data set. Now, there are two types of errors in a support vector machine. So, of course, there is the empirical error minimization component, which is exactly the same as the perceptron. It minimizes it. We, we, we measure how much error a particular example gives for a given discriminant by using the hinge loss function. But together in a support vector machine, we also want to minimize the sum of the squares of the weights because that gives us regularization. So you can think of the evaluation bit, this E bit, to go from the representation into this mathematical form that we've already written over here that we are going to then optimize using gradient descent. And we've talked about that, about if you take a gradient of this, then you get a gradient update equation, and this fit function over here essentially does the optimization. So this O bit goes over here. So that's the conceptual mapping. And it requires, of course, the training data and the test data. Sorry, the training data and the matrix and the training labels. And that's what we are doing over here. So we iterate over a number of steps Within each step, we compute if there is an error. If there is one, we use the gradient descent update based on the equation that we had obtained in when we calculated the gradient updates, and we keep on doing that until either we run out of the number of iterations or we have a we have a solution to the classification problem. So in this case, the difference between a perceptron and a support vector machine is that we are also changing the weights based on this particular part. So that's the regularization update component of the support vector machine. So I hope this gives you a better understanding of the code. This is how this code can be used. You have a set of training examples, you have the corresponding labels, you create an object, and now it's important to specify a small enough step size, specify a lambda value which is non-zero. If you set this to zero, you won't be getting any updates in the weight. So that way you can convert this into a perceptron, and at the same time you can specify a margin of zero if you want a pure perceptron that was built in the 1960s, where it was proposed in the 1960s. Okay, so you pass the training data to the fit function, and then you essentially get an object which you can then use to score or obtain predictions for a given test example or a set of test examples as we are doing over here. And then this plotted functions allows us to visualize the same thing. Okay, and we have seen how this code works, and we've seen that it gives if you use a perceptron, that is if you use lambda is equal to zero and a margin is equal to zero, then what this gives is this line. However, if you use the same code with a small enough value of lambda, let's say 0.1, and if you give margin of 1, then this makes it a support vector machine, and you get a very good, uh, almost perfect margin between these two classes that you see on your screen. So I hope this code helps in promoting your understanding of support vector machines. Please go through the code on your own and try to understand it better. You can, if you just want to use support vector machines and not worry about any of the mathematics that we've talked about, Sklearn, the scikit-learn library in Python, has a very good package on support vector machines. It's called linear SVC or linear support vector classifier, and we'll be importing that as an object called classifier. We have a training data set over here, which is essentially the OR classification problem, or classification problem, in which we have 4 examples, and these are the corresponding labels. What we do is we build a classifier. It's important to specify class weight is equal to balanced, and we'll talk about why that is the case, but don't worry about it right now. This is related to if there are more examples of one class and a smaller number of examples of another class. So in this particular data set, we have 3 examples of one class and only a single example of the other class. So based on how the optimization is done, it's important to specify this parameter to be equal to balance so that the error contributions from both of the classes are taken into consideration equally. So error of the positive class is treated the same way as a single error of the negative class. Okay, so this is what this does, but don't worry about it too much right now. We have C is equal to 100. So unlike our implementation or simple implementation that we just talked about that uses this lambda parameter, the built-in support vector machine classifier uses C, which controls the cost contribution to the empirical error minimization and margin maximization. And you can use the same and you use the predict function to get the labels, and you can use the plotted function as shown over here to get the training labels. Now let's if you I'll give you the code. It will be posted as part of this module, and you are welcome to execute that code and to build your own understanding. But once you do that, try it with a different values set of parameters for the same training data. So if you set C is equal to 1000, you would get this line using this plotted function, this bit over here. And as you can see, this is a very good line because it maximizes our margin. As you can see, this line is equally distant from all of the training data points. So it gives a very good margin. So it has more noise tolerance, and it has better, it would have better generalization to unseen data. So if you use C is equal to 1000, you get this line. But if you look at the weight values, which you can do using what is called CLF dot coef underscore and CLF dot intercept. So this gives you the weight vector, and this gives you the bias for this support vector machine. And if you use set C equal to 1000, then you can get the weight values or the weight vector of 2, 2 and a bias equal to -1. Now, before you move on to changing the parameters, think of what should happen if you reduce the value of C. And we've talked about that. We've talked about the role of C, but I want you to pause the video and think about why these, or what should happen when you see the set the value of C to be a smaller value. And then you're welcome to discuss this with other colleagues as well, and develop a mental understanding of why having a small c, or what would be the effect of having a small value of c. You can also execute the code and of course find those values out. And once you do that, you would see that for c is equal to 1, which is 1000 times less than the c value of 1000, you get the weight vector, which is, if you think about it, these weights are much smaller than this weight. And that is the desired effect that should happen when we set a small value of c. We should have more regularization, so the weights, the individual weight values should become small. But if you look at the line itself, it doesn't really change much. The line is still at the same location it was previously. But what has happened, if you pay very close attention to the shading that you see in this color space, that has changed. So the effect of having a small value of C is now that the weights are smaller. That means a small change in the input is not going to produce a large change in the discriminant function score. So these scores now change more smoothly, which is why you see a sharper transition from this purple color, and within this purple color between the different classes, whereas that has now reduced in this particular plot on the right. And if you look at the color, then that relates to the discriminant function score as indicated in this color bar. So the effect of reducing the value of C is now that you get a smoother classifier, and that is the effect of this parameter C. I welcome you to try out and understand the role of C and lambda by executing both of the codes, so that you're a master of both of these, or master of the concept of regularization and hyperparameters in both of these formulations of the support vector machine. Okay. So next, what we are going to talk about is going to be about margin, but at this point, you can probably go ahead and try the code that you've been given, or the set of codes that you've been given, to gain a deeper understanding of these hyperparameters. Thank you.